So welcome everyone to Optimization in Oslo. Today we're very happy to have Professor Harbir Antil from George Mason University. Harbir has a lot to say today. He's going to talk about optimization, digital twins, and augmented Lagrangian methods, and how that all fits together. So Harbir, the floor is yours.
Thank you, Thomas. So, and thanks for this kind invitation. I wish I was there in person, but hopefully someday. I've never been to Norway, so it's going to be exciting actually to visit you there. And it's really nice to see, Thomas, you're really starting this initiative, and which has got a lot of traction recently. I know it was a challenging move from Germany to Norway, but I mean, I know Thomas for many years now, and we've jointly working on several projects and organizing seminars all over the world, including a couple of them in India. So it's really a pleasure to participate in and give a talk in this seminar. So there is a lot going on in my talk, and I can stop whenever you guys want. But let me start. So this work is partially supported by National Science Foundation, Air Force Office of Scientific Research, DARPA, and DTRA here in the US. So the focus of the talk is more on optimization, in particular PDE-constrained optimization. I'm going to try to give a slight twist to PDE-constrained optimization. You can see my second slide, Thomas, right?
Yeah, we can see it.
Okay, good. Sometimes it pauses.
Yeah.
Sometimes it pauses. So I'm going to try to bring in this concept of digital twins and try to couple it with optimization. So what is a digital twin? I will not try to define it because the definition is still not completely clear. Basically, in what I call the first generation or the previous generation, the last, I don't know, 5-6 decades, people have been doing mathematical modeling, simulations to emulate some physical phenomena. But this has been challenging, and the reason being that many of these.
That's better.
Okay, so but this has been challenging because many of the processes in nature you cannot describe using physical principles, and in addition, these problems can be so challenging that previous generation of computers you weren't able to fit this problem on them. Then in the last decade or so, there has been so much push in just using data and try to create a digital model out of this data. And one of the main reasons why this revolution is coming up is because these days sensors are cheap. So you can place sensors wherever you want, gather data, try to create a model out of that. And then, use machine learning. But this is not completely reliable approach either, because it does not take into account any of those physical principles that people have worked on for decades. And now there is a strong push in the so-called digital twins, where one tries to combine these data-driven approaches and physics-based models. The idea is basically that you place sensors in different places, you gather data from the sensors, and then you have like a digital model, and then you couple it with a physics-based model, and then you go back and forth between them. There are many challenges. One, try to use machine learning, UQ, optimization under uncertainty, reduced error modeling. This is sort of a mix of everything at this point. And at this juncture, it seems that engineers are truly leading this field. And now the questions are coming up: what role can mathematics play in this direction? In fact, to address some of these questions, we will be organizing a workshop in December. It's an NSF-funded workshop from December 11 to 13 here at our university. So let me give you one sort of a very basic example of a digital twin. This is an example from a recent paper, which is available now on arXiv, together with my colleague, a PhD student of mine that I'm co-supervising with Professor Lohner, Facundo Arudo, and Roland Wuchner from Braunschweig in Germany. So this is an actual bridge. I think it's from Latvia or Lithuania, I forgot which country, where we have placed certain sensors on the bridge, and we are receiving some measurements from these sensors. So these little balls, they indicate the sensors. And what has happened in this bridge is there is one of the beams is weak, and the goal is to identify from the sensor measurements which portion of the bridge is weak. So this you can cast as an inverse problem or an optimization problem with PDE constraint. In this case, the PDEs will be elasticity equations. I'm going to come back to this example later on. This is sort of a motivation of a digital twin. Other important aspects. So now we already see optimization problems with PDE constraints in a real life scenario. You've seen this crane in many places, right? When we are doing construction, for example. Again, what has happened is that we have a crane, we have placed some sensors. These dark blue dots indicate the sensors, and we are trying to basically get this sensor measurements and then try to match the sensor measurements with the output of a physical model, which is given by elasticity equations. I tried to solve this problem by some random initialization for my optimization algorithm. I get results of this type, which is far from what I actually intended to do, because my goal was to get a uniform strength factor of 1, but I get something really nasty. And here, what the aspect that I'm trying to bring up is that what we have done here is what we have not done is we have not used appropriate inner products or scalar products when we try to solve our optimization problem. And I'll specify later on when I try to have a fix to this problem. So there are many layers when it comes to optimization problems with PDEs related to digital twins. These are large scale problems. You have to respect the appropriate function spaces to get correct results. Another aspect, which is an article that we just submitted with, it's a short article that we just submitted with Facundo and Professor Lohner, is that many times in these models, and I'm sure Thomas will appreciate this because he's done a lot of work in this direction, that there is a lot of uncertainty in these models. You can have an uncertain load, for example. There could be sensor errors. There are measurement errors. If you try to, let's say your goal is try to identify this weak spot in your plate, and from these sensor measurements, which are denoted by these dots, if you try to use the standard expectation, if you try to minimize standard expectation subject to certain constraints, you get a very non-optimal result. So eventually, I'm going to show another slide where we try to fix this result using some of the results that Thomas has developed. All right, so now another area that we are focusing on is, so these are digital twins or sort of digital twins in structural engineering, but you could try to create digital twins in biological models too. So in this project, together with my colleagues here in bioengineering, what we are trying to do is we're trying to identify the flow inside an aneurysm. This aneurysm may occur in brain or in heart. And the challenge is that, how far downstream you should model the veins, because that, and what boundary conditions you should specify. And this has a significant impact in the type of flow that you obtain in your model inside the aneurysm. So this is another type of digital twin, but also a PDE constraint optimization problem, but the physics here is given by fluid dynamics equations. So many of these problems you can fit in this general framework of optimization problems with PDE constraints, where I try to minimize an objective function J. U is my state variable, fulfills a certain PDE or an ODE. Z is my control or my design variable. As I said, in PDEs, you may have some uncertainty. For example, here indicated by omega, in that the structure example, we had uncertain load, for instance, or uncertain boundary conditions. This leads to a random variable objective function J, which you can scalarize using a map R. Previously, I mentioned expectation, but one could use some general risk measures as well. So there are two set of problems. One is a deterministic problem. One is an optimization problem under uncertainty. And the goal will be try to solve this type of problems. I already gave you several examples, but let me give you a much more precise example. This will be related to permeability optimization. This is somewhat a classical problem, but in many ways it is not, and I will describe that shortly. Then I will discuss a very generic optimization framework called Augmented Lagrangian SQP type method to solve generic optimization problems. And then I'll come back to some of these applications that I mentioned earlier. All right. Let me start with this permeability optimization example. This is a joint work which is currently in review with the folks at Sandia National Labs, in particular, Drew Curry, Dennis Riesdahl. They are optimization folks, and Dan Robinson and Meher Salam. So what is the goal? Here again, we are kind of looking at a digital twin problem in the same realm that the problems that I discussed earlier related to structural engineering. The goal is to design such devices. These are three-dimensional devices here. If you it's like a ball, for example, but there is some inflow here at the inflow boundary, and there is outflow at gamma out. And the flow respects the Darcy's law. U is the velocity, P is the pressure, kappa is the permeability, and mu is a constant dynamic viscosity, and you have incompressibility constraint. Now, what is the goal? The goal is, try to design devices allowing uniform distribution of fluid. So we want what we want the fluid to follow certain streamlines. We want to match a desired velocity profile U sub D. This kappa or mu grad P is the Darcy velocity. Again, P is the pressure, and P fulfills this equation here, now written not in the mixed form like here. So the question is, what is the precise formulation? What domains one should use? So for this problem, coming from this engineers, we are going to be working in the axisymmetric domains. So we're going to map our 3D domain to two-dimensional using cylindrical coordinates. And another question is, how do you design the desired velocity profile? The idea will be that velocity profile fulfills certain principles, that if two particles enters the domain at the same time, should exit at the same time as well. They should fulfill incompressibility constraint or mass conservation. And there was one more. I forgot about that. I'll come back to that. So, but these are like the two key principles. And in addition, our optimization variable will be kappa, which will be what we call the permeability of. That's why it's called permeability optimization problem. And kappa is not a constant, but it's a function. And we need to establish how we, in what sense, we have convergence, and in what sort of function spaces. I will describe that shortly. Eventually, we need to discretize and come up with an optimization method. So this is a much more specific optimization problem. So in order to solve this problem, we're going to borrow some ideas from topology optimization and in inverse problems. So related problems occur in topology optimization, where somebody tries to design of binary porous microstructure or channels. And we're going to be borrowing some ideas, and I'll be precise about that in a minute. Similar problems also occur in inverse problems, like the one I described at the start of the talk, for instance. Typically, one tries to do point-wise matching of displacement or pressure for the inverse problem, but we are trying to match the gradient of the pressure, which is the Darcy velocity. This permeability optimization, there has been some work by our collaborators previously, but it was not very mathematical. And so the goal is try to develop a whole mathematical theory around this work, and motivated by this mathematical theory, we come up with new sort of experiments. So here is our problem now in the full glory. We try to minimize objective function J. The optimization variables are pressure, kappa, permittivity, and we also have another optimization variable, which is the magnitude of the velocity, C, but I will not talk too much about it. This function W is just for scaling purposes so that everything is non-dimensionalized. Part of the boundary has Dirichlet boundary conditions. Part of the boundary has Neumann boundary conditions. So here I'm writing my problem in the so-called weak form. So I took the previous equation, multiplied by a test function, did the integration by parts, and I get this equation. In addition, I want to make sure that my operator is elliptic. For that, I need to enforce certain constraints on K given by C1 and C2. Since we'll be working in axisymmetric domains, so I need to map everything, this three-dimensional domain to 2D, which is little omega, using the cylindrical coordinates. This is somewhat standard, and then we get a sort of this is our admissible constraint set. So as I said, we need to there are many challenges. One is how to specify this desired velocity profile. You need to you want the desired velocity profile to fulfill certain principles. It should be mass conserving. It should be this time consistent, or it should lead to uniform time, which is like two particles entering the domain at the same time should exit also at the same time. The flow should follow certain streamlines. So this last one was the one that I forgot earlier. We need to establish existence of solution to our problem, but this is challenging because we have terms like kappa, gradient P, both in the PDE and in the objective function. And if you think about kappa, we're not enforcing any smoothness on kappa, is just in L infinity. So you can at best guarantee convergence in weak star sense in L infinity. P is in H1, so you can guarantee convergence of grad P in L2, which is not enough to pass to the limit. One could try to use this notion of H convergence, which has been built and by Tartar and Mura. But the issue with this approach is that it's not structure preserving, that you may start with something which is scalar valued, but may end up with a matrix valued object here, this capital K. Instead, what we will do is we'll, motivated by topology optimization, we'll try to use a filter to build enough compactness to make sure that this term converges in appropriate sense. So this kappa n or this f kappa n will be in H1, which converges strongly in L2. Basically, that's the idea. This will solve another PDE. All right. So what is our filter? Basically, you take your kappa, which is solution to your problem, and then you pass through this Neumann equation. Delta indicates the filter radius. And then for axisymmetric domains, irrespective of the angle, so you can work with even convex, non-convex domains, you have enough smoothness that this solutions have certain regularity, which is S3 ½ plus epsilon, that's compactly embedded in continuous functions in 3 dimensions. In 2 dimensions, it's not an issue at all. In addition, now we need to make sure that this, kappa fulfill those bound constraints to preserve ellipticity. We want to make sure that this kappa tilde fulfills similar bounds. And you can build a maximum principal type argument using some cutoff functions to ensure that this f kappa fulfills related bounds. And then just by the direct method of calculus of variations, you can establish existence of solution to your problem or the filtered problem. This is not an issue anymore. All right, so how about we try to solve this problem? So we can write the problem in the so-called weak form, not the weak form, in the reduced form. where we define a map or control to state map. And then our reduced problem is, I've eliminated the PDE constraint. They're implicit. We can establish that our reduced objective function is twice continuously Fourier differentiable. Therefore, we can use gradient or Hessian-based algorithms to solve this problem. From the discretization point of view, we use piecewise linear finite elements for both P and kappa tilde, which is our filtered permittivity, permeability, and piecewise constant discretization for kappa. Now, at the continuous level, I was able to establish that this F kappa, the filtered permeability, fulfills those bounds using maximum principal arguments. But then we need a similar maximum principle at the discrete level for piecewise linear finite elements. Even in the classical setting where you're not working in the axisymmetric domain, we are not working the cylindrical coordinates. To have this maximum principle fulfilled at the discrete level, you need the so-called acute angle condition on the mesh. And my colleague Dennis, he's really good with such things. So he managed to create this meshes with acute angle condition. And now we're talking about 2 dimension, right? So we have a proof for this in the classical setting without the cylindrical coordinates. But in the cylindrical coordinate setting, we saw numerically that we do fulfill this maximum principle, although we do not have proof for this at the moment. All right, so let me show you a couple of numerical examples. So here is one of those pictures from earlier, which is our domain. We are looking at the axisymmetric domain. Our goal was to follow these dotted streamlines. And what optimization gives us is these colored lines, and we are clearly following them in a nice way. At the bottom is we see the so-called transit time. If you do not do optimization, you get this red dotted curve. If you do optimization, you get a sort of a constant transit time. That was one of the goals, right? 2 particles entering the domain should exit the domain at the same time. Permeability field look like this. I guess this is interesting enough for our engineering colleagues. Eventually, they want to do some sort of 3D printing for these things. One could do non-convex domains too. And here our goal is to follow these dotted streamlines. We get a permeability field, which is like sort of piecewise smooth. It looks super interesting, I thought. And the transit time, again, is constant if you do optimization. If you do not do optimization, it's this red curve. So what we have done here is, right, we try to match, we created a velocity profile, which is not trivial to construct, actually. More details are available in our paper. But we want this velocity profile to fulfill certain principles. And then we try to match this velocity profile subject to our Darcy equation as constraint. Our optimization variable is the permeability. We have shown existence of solution rigorously. We established that our objective function is twice continuously Fourier differentiable, and then we can create an optimization algorithm. All right. So this sort of brings an end to the first 1.5 part of the talk. Now I'm going to switch gears, and so this was very specific examples. So PDE-constrained optimization has many flavors. One of the flavors is optimization in function spaces. This is a very generic optimization problem at this point. We're trying to minimize f of x. This capital X could be a finite dimensional function space or an infinite dimensional function space subject to some PDE constraints, gx equals 0. And then we have additional inequality constraints. There could be a number of these constraints on different components of X, for instance. We need certain properties on F and G. F, we need them to be continuously Fourier differentiable, for example. There are some other technical assumptions that we need in order to be able to guarantee convergence of stationary points later on. And I've introduced this map T for some technical reasons. What we need from T is this needs the dual of this, or the adjoint of this, needs to be injective. This framework does apply to PDE-constrained optimization problems of the type that I introduced earlier, where we try to minimize F. U is my state. The state was P in the previous example. Z is my control. In the previous slides, kappa was my control. And we have equality constraints. We can have inequality constraints on the state or on the control C. Now, these type of problems are extremely challenging. And why is that? So, because these are really large-scale optimization problems. So one may not want to solve these PDEs explicitly in every optimization iteration. And there we're going to use this framework of Zymes and Ulbrich and Eichenschloss and Riesdahl, where we do not try to solve the PDE explicitly in every iteration, but we solve it up to a certain tolerance. So we have inexact solves. In addition, we want to take advantage of appropriate preconditioners to do these subsolves during our inexact trust region SQP framework. The catch is that this framework has been traditionally used for equality constraints, and it works very well. But now we have additionally inequality constraints. So what we are proposing to do is to augment these inequality constraints using augmented Lagrangian. And other thing that we are proposing is you use separate penalties for separate constraints. So the state U could scale very differently than the control Z. Think about U being the temperature, fulfilling the heat equation, Z being the source, which is the force. They have completely different units, and we see this in the numerics too. So in our framework, we are proposing to use different penalty parameters for different variables. And all this is published in this recent SciOpt paper. Let me show you a quick example, which is sort of a textbook example. So you have a semi-linear PDE constraint. You're trying to match U sub D. This is some desired, let's say, temperature. Z is my control, which lies on the right-hand side. I have constraints on the state. It needs to be above a certain bound, U sub A, and I have some constraints on control. And what I'm trying to depict here is that this is actually a very challenging problem because I don't know if you're familiar with it, but if you're not, let me say it quickly. This condition needs to be understood in the sense of continuous functions. So then the Lagrange multiplier corresponding to the state constraints are actually measures, and you can see this numerically, sort of this faint line, which is a measure actually. The Lagrange multiplier corresponding to the control are L2 functions. So we know we have a very large scale problem. Now we have to approximate all these measures and everything. So there is a lot going on in the problem itself. Now, let me try to give a quick derivation of this augmented Lagrangian that I mentioned. Again, we are going to keep the equality constraints explicit, and we will augment the inequality constraints within the augmented Lagrangian framework. So I'll quickly recall the definition of the indicator function, which is written here. If you're in the set C, convex set C, then the indicator function is 0. If you're outside the set, then this is infinity. I can rewrite my problem equivalently. Again, this is exactly the same problem as before. I'm just adding this indicator function to my objective function. Now I'm going to use some convex analysis. And this approach goes back to Rockefeller in 1976. Although it's not written explicitly in this form in many places, I recall that this C is convex, so indicator function is convex. Its double differential conjugate is the indicator function itself. And by the definition of this differential or the conjugate or the Legendre transform, we have such an object. And now if I regularize this using a quadratic regularization, then my this objective function here is strongly concave, and I can explicitly write the so-called multiplier updates in augmented Lagrangian, where P indicates the projection onto this set C sub I. And this leads to my usual augmented Lagrangian functional, where I have these added terms now. F was my original function. And remember, we're still keeping the equality constraints explicit. So our subproblems look like following. We want to minimize this Lagrangian L subject to this equality constraints. And this is where we can use this trust region SQP, this inexact trust region SQP method that I mentioned earlier, which has been very well tuned for last couple of decades. So we might think that we are in a good shape. However, when we saw these papers, they always assume this L to be C2, which is not the case in our setting, because we can at best guarantee C11 smoothness because of all these projections. So in the simpler case, think about the L2 norm of the max or the min. You cannot guarantee that to be C2, but you can say that it's C1. But it turned out that if you go through the theory of these articles, that in fact you do not need C2 smoothness. It's enough to have C11. Additionally, this L carries some more properties depending on how F look like. So if F is lower semi-continuous, you can establish that L is weakly lower semi-continuous. If F is convex, I did not assume F to be convex, but if it is convex, then L is convex as well in the first argument, and also the differentiability properties it carries. There is a quick snapshot. I will not go through details of this algorithm here. We have, remember I mentioned that we are not solving the PDEs explicitly, but we solve up to a certain tolerance, which is not fixed upfront, but it can vary. And then we have, our first order condition, which we solve up to certain tolerance epsilon. If we have certain constraint violation, we update our penalty parameter, which is R sub I. Remember, different R sub I indicates different constraint. Otherwise, we may want to update our Lagrange multiplier. So it's very similar to your typical augmented Lagrangian, but put in this framework of Kohn, Gold, and Twant. And the difference is that we are not, those guys, they penalize the equality constraints, but we are penalizing the inequality constraints. So just to compare this with existing approaches, so our approach, it encompasses multiple penalty functions to handle variable constraints. This approach is related to this so-called Lancelot, which is a well-known, well-established method, but it's all in finite dimensions. And it penalizes the equality constraints. We are penalizing the inequality constraints. We have different penalty parameters corresponding to different constraints. In this article, or this algorithm SECO, it tries to penalize the inequality constraints, but everything there is also in finite dimensions. In infinite dimension, there are some approaches, in particular, this works from the Würzburg group in Germany, where, but they still penalize the equality constraints. They do not allow inexact solves during the iterations. So what our method is, basically, in summary, is an infinite dimensional version of SECO with inner workings of Lancelot, multiple penalty functions, inexact linear solves. What about convergence? We can establish convergence of the method as well. Let's say we have, certain thresholds on the PDE constraint, on the first order condition, on the inequality constraints. Either this method converges in finite number of iterations, or it produces an asymptotic stationarity condition, which kind of look weird, especially the second condition. But in this super general setting, this is all what you can guarantee. But in a more specific scenario, what we can show is that our strong accumulation points are stationary. But in PDE optimization problem, you may not be able to guarantee strong accumulation points always. You can only have access to weak accumulation point in general. However, this method immediately converges in finite dimensions. In case of weak accumulation points, in many scenarios which are more realistic, that is, if you have one penalty or this map that I introduced, T is completely continuous, maps weak topology to the strong topology. And this is the case in many of the PDE optimization examples, that we can show that that weak accumulation points are feasible. We can also extend this theory where this map T is not linear, but it's non-linear. For example, if you have complementarity type constraints, which I will not discuss further at the moment. Let me show you the same example that I mentioned earlier, where we are trying to match this function U sub D. Z is my control. U solves this semi-linear equation. We have constraints on U and also on Z. We have around 2 million optimization variables, around 1 million equality constraints, and around 3 million inequality constraints. And I mentioned, right, we use different penalties for different type of constraints, and it really it should really be the case, because you see the penalty parameters corresponding to the state constraints are blowing up, but the penalty parameter corresponding to the control, they remain bounded. So they have completely different scaling. Sorry, these are these penalty parameters R sub I. So we had two control constraints, lower bound and upper bound, and we see that they don't blow up. We start with something like 10 to the minus 3, and then they remain in the order of 1. And this one, you start large, and it keeps growing, which makes sense because the Lagrange multiplier corresponding to the state constraints are radon measures. So here's a quick table. So each row corresponds to a different finite element mesh discretization, 64 by 64 to 512 by 512. This first 3 columns indicates the example where we only had the constraints on Z. Second one, where second block, we had constraints only on the state, and in the last block we had constraints on both state and the control. We see that number of augmented Lagrangian or the outer iterations are relatively small. The inner iterations are SQP, and the workhorse is CG. They also remain relatively small, and we see nearly mesh independent behavior. All right, so we can extend this work, and which we are working on with Thomas actually, to this risk-averse optimization problems that I mentioned earlier, where now we have uncertainty. Let's say in the PDE, we may not know some boundary conditions or some load. This leads to the random variable objective function, which we scalarize using this map R. What are the examples of R? I mentioned expectation, which is a risk neutral measure, or one could use more general risk measures like mean plus semi-deviation, or so-called conditional value at risk. And the idea here is that we not only add a quadratic penalty to the inequality constraints, but we also had a quadratic penalty corresponding to this risk measure. And this idea comes from a recent article of Thomas and Curry, primal dual risk method. So I encourage you to look at that article. All right, so this sort of brings a conclusion to the second part of the talk, which was more focused on designing an algorithm, augmented Lagrangian algorithm, to solve very generic class of optimization problems, including some of these examples that I mentioned at the beginning. Now let's look at some of these applications again. So I mentioned that one has to be careful. In this crane example, the catch was, what was the problem? Let me recall it again. You had certain sensors, you're getting some sensor measurements, and you're trying to match the displacement or the strain measurements that you're receiving subject to certain elasticity equation as constraint. We try to solve this problem blindly without respecting the function spaces. We get such a result, although we wanted a uniform strength factor like this. If you realize that your problem is your gradient is in the dual of your H1 Sobolev space, and then use the appropriate Rees maps, and you get a result like this. So again, the purpose of this slide is to make sure that when you're working with such problems, you respect the appropriate inner products and use the appropriate Rees maps. And I mentioned this example earlier where we had a plate, a part of the plate was weak, and we had certain sensor measurements. If you use the expectation, and here the uncertainty occurs because of the load and the measurements. If you use the standard expectation, if you minimize the standard expectation, you get a result like this. On the other hand, if you use this risk measure with different beta, the larger the beta, the more conservative you are. You get pretty interesting results, actually. So,
Harbir, what is X in this example?
Is it the quadratic functional?
Like misfit from the data, or?
That's correct. That's correct. It's the misfit from the data.
It's like a quadratic loss function.
Right.
And you have misfit at the little silver dots, I guess, or
that's correct. Absolutely, yes. Yes. Yes.
And the PDE is
elasticity equation. And we are searching for the coefficient in the elasticity equation.
Ah, I see.
And sorry, I should have been more precise. It was vague. So we are looking for the optimization variable is the coefficient in the elasticity equation, and the uncertainty is in the load on the right hand side.
And how many data points do you have when you do this?
You mean in the random variable?
Yeah, is it just like you have one measurement per each dot, or do you have like multiple measurements?
For this results just one measurement for now.
Ah, okay.
I just generated this yesterday actually for this talk. I thought you might appreciate this.
Yeah, no, I did. That's why I'm asking questions.
Good. All right, so this is like super fresh, honestly. All right, so coming back to that other example that I mentioned, so there is no uncertainty here in this example yet. I'm still working on it with Facundo. So we had measurements at these sensor locations, and the goal was to identify this weak part of the bridge. Here we're using this beam and plates finite elements to the discretization. And we do a pretty good job. We are able to identify this weak spot, and in terms of the magnitude of the displacement, we are not doing bad either. It looks more or less the same. All right, so before I conclude, I want to mention another application that might be of interest to you guys. This is also very, very recent work. And it's kind of different than things that I introduced earlier, but fits in the same framework. So traditional cameras, they capture, you could look at your cell phone, you capture one frame at a time at a fixed rate. right? So this can be very memory intensive. Each picture these days is like 12 megapixels or something, and it can be very um, non-efficient in terms of power consumptions too. And many times these traditional cameras don't work so well when it comes to high contrast environment. For example, if you have at night street light and there's a car parked near it, the one end you can see where the light is shining, the other end you cannot see. So people are starting to work in the so-called neuromorphic imaging recently, and it has many applications, not just these toy examples that I mentioned, but in tracking satellites, for instance. What the idea is that you try to emulate the way your eyes work. So you capture these frames from time to time. In addition, you capture the change in the frame. So if your intensity of your pixel relative to the intensity of the pixel the previous time, the log of that, this ratio is larger than a certain threshold, you say you register +1. If it's less than negative of this tolerance, you register at -1. In between this minus C to C, which is C is the tolerance, you do not register anything. So again, you are registering pictures like this. In addition, you register all this data. And then after, these are called the events. So it's a three-dimensional data. And after a while, you again register an image like that. So this is sort of a new technology. And you are registering these neuromorphic events on the order of microseconds. And they are really efficient because they do not need much storage, actually. And this, right, so we develop a bi-level optimization framework, and together with the PhD student, our first paper is online. You can find it on arXiv. So we see that if you have a picture like this, the grass is blurred out. You're driving at night. You can hardly see these pillars. You cannot really see what's going on here. But when we do reconstruction using our approach, you can see that there is a tree here. Grass is looking better. And these posts are much more shiny.
We see the posts, we don't see the tree.
Sorry, is it on the screen?
Yeah. But we see the posts, so
yeah.
I believe you that there's a tree.
I think the projector adds some filter on its own. But yeah, hopefully you can believe me. So, but this example, it'll be more clear. So here, I took a pillow, I dropped it, and you cannot see like the thumb of this person. You can hardly make out if this is a pillow or not. But in the reconstruction, you can see the thumb much more clearly, and the reconstruction looks quite interesting too. So this paper is almost accepted in the Inverse Problems journal now. And we got super interesting reports, actually. So let me quickly summarize. So I started with, various motivations from digital twins from taking sensor measurements, trying to match the displacement or so these sensors could give you displacements or strains. You try to match that subject to some PDE constraints. You're trying to invert for the coefficients, let's say in your elasticity equation. Those details are available in the papers that I mentioned. They are on arXiv, were very recently submitted. Then we looked at one example in much more detail. This example related to permeability optimization. We saw that there is a lot going on in the background when it comes to PDE-constrained optimization problems. We need to have appropriate compactness to even show the existence of solutions. But we were able to do all that for this example and got some interesting results. And then we took a step back and look at a generic optimization problem and designed an augmented Lagrangian based SQP method. Briefly discuss some extension to risk-averse optimization, which is ongoing work right now. And then came back and discussed some of those examples in structural engineering, and also introduced this notion of neuromorphic imaging. So thank you very much.
Thank you, Harbir. So before I ask questions, are there other questions? No? Okay, I'll start then. So thanks for the very interesting talk. I guess the first question I'm curious about is, so with these digital twin models that you can relate to PDE-constrained optimization, is it usually the case that the decision variable or whatever it is that you're trying to solve for is inside the differential operator? So it's usually not like a simple right-hand side perturbation?
So far, what we have looked at, and what Roland, so this guy, Roland Wuchner, I mentioned, he's actually advising the German government on digital twins. So, and some of these thoughts came from him actually. So, so far what we have seen, especially when it comes to structural engineering, that it's, trying to identify if there is a weak spot. So all these things that I showed you, so these are so-called as strength factor. So this is how the coefficient look like in your elasticity equation. So to identify the weak spot, you have to identify this coefficient for this type of applications. There could be some other applications where what you are inverting for is on the right hand side. I'm not denying that. But in terms of structural engineering, we have done this now for this plate, for these bridges, cranes. We have also done it for aerospace industry. I did not show those results today because I need to still get permission from my co-authors to show those results. They're very recent, actually. So far, this is all what we have done. But I think there is this field is just, starting, in my opinion. Sorry, the point I wanted to get across is there is a lot that we have already done, and we can help this community, in my opinion. Sorry, go ahead.
So just for me and everyone in the room and people on YouTube at some point, so the basic structure of these problems is you have measurements at a very, let's say, sparse number of points in the domain. And then you have, I'm not sure what happened. Did you? Okay. Oh,
yeah, I just sent you.
You have measurements at some points in the domain, and then you have some random inputs in the PDE, which I guess you use to simulate experiments. And then you figure out some appropriate loss function, and you solve this rather complex machine learning problem.
That's correct.
That gives you then for example, stiffness properties of the plate or the crane or whatnot. So they always, a lot of times they at least in your talk, it seems like they all have a very similar structure.
That is correct. So far, they have very similar structure. So the ultimate goal is that, part of the problem you can only, model using the data, and other part of the problem comes from the physics, how they interact with each other. I think this is like a very, very initial, this is like a step 0 for the moment.
Yeah, very interesting.
Yeah, so as we can already see, right, it brings in lots of aspects like PDE-constrained optimization under uncertainty. Reduced order modeling will play a critical role, which we have not really looked into at the moment.
Right. Yeah, I mean, it's nice to see that the risk measures actually sort of give you what Drew and I have been suspecting for a long time.
Yeah, definitely. So, I think what you guys developed is really, really critical in my opinion.
Thanks.
Yeah.
So in the ALESQP algorithm, you start off by saying you have multipliers that are these like points, right? These measures.
Right.
But then like the algorithm starts with a more regular, I think you call it lambda, like a more regular multiplier. So I've looked at the paper, and maybe you can help me out. So is it always the case that in order to guarantee convergence to a stationary point, that I need to let the RIs, at least for the state constraint, tend to infinity? Or is there some case where I don't have to do that?
So I think when you have just control constraints, I do not think you need to take RI to infinity.
Yeah, I believe you there.
Yeah. For the other case, you can establish, so it depends how you impose the constraints, right? So you could impose the constraints in, mean, you take this map T, right? So it maps H1 in L2 compactly. So you could try to understand the constraints in that sense from H1 to L2.
But then I don't have a Lagrange multiplier.
That is correct. So I believe that in that case, you need this RIs to go to infinity, and which we see in practice too.
Yeah, like that, and in some sense that I guess I expected that.
Right.
So it's sort of comforting in that sense. So I guess line number 12 in the algorithm will, at least for state constraints, probably be met indefinitely, right? Like if it's Z is L2, but the multiplier is supposed to converge to something in H minus 1 or an RCA, then like that eventually will always be violated as K goes to infinity, because then it's, you have to keep updating in that sense.
I think so.
Yeah, okay. Yeah, very nice. Other questions?
Interestingly, it works extremely well. So we spent 3 months battling with this issue. So we first thought, one R is enough.
Yeah.
And then, we had the results. At the start of the summer, we spent the entire summer figuring out what was wrong with the method. And then once we put different scaling, then that was it. Basically, it just killed it.
Yeah. That's interesting. I mean, I'm surprised that wasn't available in the literature. But,
we haven't seen so far, and the referee couldn't point us to anything.
Oh yeah. Okay. Very nice. Good. So it's 3 o'clock. I think we have to leave. Oh wait, there's a question in the chat. Sorry. Oh, that's you in the chat, Harbir. Okay.
That is reference to the paper, the first paper.
Right. Then thank you again, Harbir.